Okay, so we have a continuously stirred tank reactor, and this is a bad C, or coaster, which is the more fun term for it. And so then we have what this coaster is, ooh, that's not big enough. Okay, I'll take it. So that is a tank that is just continuously stirred, as aforementioned. And I'm going to let that focus because it's going to focus on me. So what this coaster has is stuff going in, stuff going out, a constant fluid level. Well, in this case, it's got a constant fluid level. And so we're given a Q in and a Q out. Actually, guess what? I lied to you. Q in is equal to Q out. And we're just given a Q, so we'll refer to that as Q from now on. And I guess I should probably write, this is a reaction from A to B. No, we're not going A to A. That's not a reaction. So we're going A to B. And in going A to B, this is an exothermic reaction. So guess what? We're not just going to be focusing on the material balance. We're going to have to focus on some energy balance too, because you don't want this tank to explode. So in order to do that, we have, I wrote this in the first place, we have a jacket. And that's full of water, and it goes, well, it goes out and then it goes in. So we have a cool water going in, and then slightly warmer water going out. So TW, I think I called it TH last time, but it doesn't matter. So if I say TH, I'm referring to TW in this case. So there, and then I'll just rewrite it. Q in equals Q out equals Q. And so what this means, since the rates in and rate out are equal, we have volume is constant. And not only is volume going to be constant, but for sake of simplicity, in this case, our rho, or density, is constant as well. And we're only given one heat capacity, so that is also constant. That's I have terrible handwriting right now because I can't write standing up. So then, in this case, we also have a concentration going in of A, because you need A to react. So we have concentration of A going in, but we also have it at a certain temperature in, because we have to now account for temperature since we're doing an energy balance. I think last homework was just materials. So for that, but also we have a CA out. We have a temperature inside the reactor, and then we have a T out. But the lovely thing is that since this is well stirred, T out is going to be equal to the temperature in the tank, and then the concentration out is going to be equal to also the concentration of the tank. So it has a random concentration of A in the tank. So that is very helpful. So the whole point of this is to find the concentration of A with respect to time, or rather the change of the concentration of A with respect to time, and the change of concentration, no, the change of temperature with respect to time. Yeah, you can't really have a concentration of temperature. Well, you could, but not here. So, and we know these to be equal to we know the concentration of A in is equal to Q times the concentration of A, or Q in times the concentration of A in, minus Q out times the concentration of A out, minus whatever's reacted. So it's in minus out minus consumed, and in this case it's going to be the volume times the rate times concentration, and that is consumption. And we know that the change in temperature is enthalpy in, or no. This isn't just change in temperature. This is actually change in internal energy. So we have to do a little fun thing rho VC, not PVC, but rho VC. So the density times volume times heat capacity, let me get out of here so you can see, times the change in temperature, and that is equal to enthalpy in minus enthalpy out minus, in this case, we have the cooling jacket to account for. So there's a term called UA, which is just the heat, like just the total amount of heat transferred to that coolant times the temperature, the warmer temperature of the coolant minus the cooler temperature going in. So that's essentially in minus out as well. Or no, out minus in this case. So that'll be a positive number. No, I lied. Okay, so this is volume times the concentration, which is actually the change in moles of product, or no, moles of A in the system. So mole A. So I neglected that, and so if you wanted to do this one already, this is an easy one to do, and that's just you divide everything by V, the volume. So it's just dCA over dt is equal to Q over V times concentration in and minus concentration in the tank, because that's the same as the out, and minus just rate times the concentration, because it's a first order reaction, just simple A to B. So there we have done the material balance. And now for the energy balance, which is slightly more complicated, but not by much. So for the energy balance, enthalpy in minus enthalpy out is also going to have to include the reaction enthalpy. So we have rate going in, so it's just rho VC dt over dt is equal to rho times the heat capacity, or density times the heat capacity, is equal to Q, which is the rate in, times the density times the heat capacity. And the only thing that's changing for in and out is T in minus T in the tank. And in this case, it's going to be just plus the reaction enthalpy, but we do account for that because it's a negative delta HR term, which is just the reaction enthalpy. And it's negative because it's exothermic, and exothermic is a release in energy, so that is what that accounts for. And since you have that, you also have to multiply it by the the volume of, essentially the volume that is reacted, so VKCA. And again, we're just going to ditto go minus UA TW minus TC. So there's that for now. And I guess there's the last thing left to do is divide everything by rho VC to get dt over dt is equal to Q, that's not Q, Q over V, T in minus T plus negative delta HR KCA KCA over rho times the heat capacity, or density heat capacity. And then the last thing is going to be minus UA, warmer temperature, minus the cooler temperature of the coolant, over rho VC. So there we have done, this is not as useful for coding. I don't know if this one is as useful for coding, I guess we'll find out. But we have both of these given to us, all of this given to us, and so that's what we find that to be. And there's just one more small thing to cover, and that is going to be K, since we're given some other terms and we know K. K is equal to a K naught term, which is, because this is the rate, and K naught is essentially a representation of the rate of collisions inside the tank. And so that is going to be multiplied by E to the activation energy, or in this case it's represented as E over R over the temperature. And I'll write all the given values down and rewrite all this stuff for when I code next. And I guess I'll just give a last minute look at this, see what I've written. So we have like all this stuff. No, I can just do this. So we have this, the givens, and then we have this and more. I can't do this to save my life. And then just the K equation. So there we have derived the material and energy balances required for the coding portion of this.